Hello, everyone. Good afternoon. Hope everyone had a good chance to eat lunch. Uh, I'm Sudhir Shrestha. Welcome to our sessions and afternoon session. I'm Sudhir Shrestha. I'm with Esri. And this session is convened by Anna Privat from Amazon and our Joe Flasher from Amazon. He's somewhere here, I guess. I saw him. And welcome everyone. And apologies for the constructions. That is something I cannot control. But hopefully everybody had a lunch. There was like a chicken ran out. So welcome everyone. So we have 6 really excellent speakers talking about some of their work. And with that, without further ado, I would like to invite Anna for her talk. And I also would like to acknowledge our help from the Devon is out here, our community fellow.
Okay, thank you. Let's just put this. All right, thank you everybody for joining us today. Okay. Do you want to do that?
Share the screen. Does it work now?
Is that it?
We're good?
Is it working? Okay, perfect. Thank you. Okay, great. Thank you, everybody. As Sudhir said, I am with Amazon. I'm actually with the sustainability team at Amazon. I'm a senior program manager, but I'm also the lead for a program that Amazon launched last December called the Amazon Sustainability Data Initiative. And so I will take a few minutes just to give you a quick introduction to the program, and then we'll have a set of different speakers, including some of the collaborators and customers that we are working with through this program. So let's see if I can move this. Okay, thank you. Okay, so a little bit of context to why we're doing this and what is the motivation behind it. So I was trained as a scientist and as a researcher and spent most of my career at NASA and NOAA working in the space of environmental issues and doing research in remote sensing. And from my experience and everything that we all, most of us in this room can experience as well, what we see is that we have more data than ever, right? We have more data spread everywhere in different catalogs, but that's not necessarily manifesting itself as more meaningful and timely insights for sustainability, especially, right? And so there's all these pressing issues that we need to address, from climate change to food security and disaster response. And so more than ever now, we need to optimize the process from data, raw data, all the way to insights that can support decision making. So it's based on this concept that Amazon put forward, the Amazon Sustainability Data Initiative. And what we're trying to do is really, how do we reduce the cost and the time and the technical barriers associated with generating those insights? And how can we leverage the Amazon scale and the technology and the cloud and all this experience that we have to actually support the community in innovating and problem solving in the space of sustainability? What do we move forward with this? And what is our at least our initial plan is to build this ecosystem for change. And we're focusing in 3 primary areas. We believe that if we enable better access to data and to analytical capabilities, as well as to knowledge, technical knowledge about to leverage the cloud, we can potentially create a space where it's easier for people to innovate in this space. And in very practical terms, what does that mean? In terms of the data, we're trying to enable better access to foundational data. So the idea here is not for us to recreate a catalog with all the data in the world for sustainability. That's not the purpose. What we're doing is working with the community, and this is a very community engaged project. Work with the community and a lot of the AWS customers that are already working in the sustainability space, and try to understand what are the needs that the community has, and what are those foundational or key data sets that if we democratize access to and bring to the cloud, will potentially unlock much more innovation in this space. So we are working that through the public data set programs that some of you might be familiar with, that Joe Flasher is a key partner in that project. Well, he's part of this project as well. And what we do is basically we provide storage and egress support to data sets that we think are of value for the broader community to have access to. And we don't necessarily go and get the data and bring it to the cloud. What we do is primarily work with the data providers or brokers that will bring the data, and they retain complete control and ownership of the data. Okay, so that's in, okay, let me see if I can minimize this. All right. So these are just some of the examples of type of data sets that we have now. I believe currently we have about 54 curated data sets. So again, the idea is not to just bring the entire universe, but the data sets that are critical, that we hear are really critical for this space. And we're covering weather observations, forecast data, climate data, air quality, and so forth. Okay. All right. The other aspect, as I mentioned, is democratize access to the analytical capabilities. Okay, now even if we ideally identify what are those foundational data sets, we put them in the cloud and make them accessible to anybody. If we really want to go to the point where we are deriving meaningful insights, we need to have compute next to it, right? So, and that's the part where the cloud can provide a lot of existing services and capabilities that can help the community move forward. So, as part of this program, we're leveraging existing programs and exploring new ones to, for instance, to provide cloud credits to anybody that has an idea and they would like to prototype it in the cloud, as long as it falls under the space of sustainability. So that's one of the things we're making available through the initiative as well. And then the third one, as I mentioned, which is really as critical as the other ones, is to recognize that there's still a lot that we need to learn as we move like legacy code to the cloud, as we create new solutions and workloads. And I think we can all do it much better together, like in situations like this, in groups like this, where we can bring our knowledge, share it, and grow it faster. So one of the things specifically that we are doing with the ASTI, or Amazon Sustainability Initiative, is create a community of practice. And that helped us not only understand what are the needs, because we are very focusing on coming from the customer space or the user space to solve and mitigate the challenges, but also we are trying to produce a lot of information and resources that will help the community grow as well. So anything from creating blog posts where we expose innovative ways where customers are using the cloud and open data for sustainability, tutorials. We host several meetings to bring people together and things like that. So these are just an examples. Right now, I'm just going to very quickly go through a few examples of types of projects and activities that we are collaborating with or supporting, and just to show the diverse space. You know, sustainability, as you all know, is like a very broad space. So it's kind of hard to put boundaries, but anything that falls in the space of environmental issues or even social responsibility, obviously, any of that falls under sustainability. Okay, quick example, CalAdapt is a project in California, is very focused on supporting the community in identifying the data and the information they need to understand climate risk and adapt to climate risks. Another one is StormSense. It's a very different kind of project and platform, but also, you know, in this case, it overlaps in the sense that is looking at inundation and flooding and the impacts of sea level rise in the community in Virginia. Another one that is, this one is international, so I didn't mention, but really the program is global, and we're trying to look at really promoting innovation globally. In the case of African Regional Data Cube, for those that are not familiar with it, it's this concept of using the Data Cube technology in Africa to enable countries there to access more remote sensing, primarily remote sensing at this point information, to help them with things like detecting illegal mining or deforestation and expansion of urbanization and things like that. And it was a very successful prototype in a sense that now is being scaled into a continental-wide project called the Digital Earth Africa. So for those that are interested, it might be worth exploring that. Very different one, for instance, in this case, it's a startup group in India that is looking at modeling air quality for different cities in India. And we are working with them as well. And then some of you, or maybe most of you, have heard about PenGeo, and they had several presentations in this meeting. That's another group that we're working with and trying to support. And finally, I'm going to mention the Blue Dot Observatory, and we're going to have a follow-up presentation by Grega that will tell you more about it. But it's really a good illustration, as well as how, open data and cloud technology are really enabling us to look at things in a different way and to unlock insights and knowledge that we didn't have before. And we're really excited to be part of this process, and we want to enable it as much as possible. So that's it. Thank you. And Grega? I don't think we have time for questions for me, right? Let's just maybe save it for the end, or what do you want to do? Okay. Does anybody have any question? Okay. We'll just run to Greg, if you don't mind. Awesome.
So, like a year and a half ago, a story hit the news that Cape Town in South Africa is just about to get out. I mean, that they will not have access to the water anymore because they had a really problematic year or 2 years, and the main reservoir that they had was more or less dried out. Here you can see how the water was vanishing through 2017 and 2018, but then luckily in 2018, in second half, it was actually there was enough of rain that it actually got water back. And I mean, if previously they were literally counting down the days or weeks when they will get out of the water, they kind of got lucky, and they diverted the major disaster. They still have significant issues, and they have like restrictions on what they can do and how much water they can use, but at least they have water, right? But then if Cape Town was lucky, the Chennai in India, like a couple of weeks ago, another story hit the news that they ran out of water actually. Here you can see their main reservoir, so it's like a 7 million people city, I think. And basically they got out of water, and now they have to walk to some remaining parts where they can actually find some water, and they need to carry this back. And I mean, unfortunately for them, it seems that they are not getting that lucky as the Cape Town did, because the monsoon that is coming it will probably not be powerful enough. And it's not just Chennai, but it seems that most of India and many other parts of the world are affected by the climate change, will have problems with the water. And that's something that I guess that we living in a developed world kind of forget, like water shortages in these parts is like you can't wash cars and you can't fill the pools, but nobody is thinking about not being able to take a shower or even cleaning the hands after taking a toilet. And I mean, these things are really, really important. And I think that we should all think more on how this is affecting the world. Now, a couple of years ago, Google and Joint Research Center, they joined forces, and they did an analysis of a couple of decades of Landsat data, and they calculated for each and every pixel in the world whether there was water over some period of time or not. And they created this global surface water explorer. And basically what you can do is you can click on any part, for example, in the lake, and you can see whether there was water over some period of time. And now if you click on the northwestern part of the same lake, you see that the water was going up and down, that it was not always present. And I mean, that's a super nice tool, probably more focused to the scientists than a general public. But same as with many other research projects, it had a problem that after the project ended, simply they didn't update the data anymore. So like for many years, it was only available until 2015. Now I've seen just a couple of weeks ago, they updated it, and now they have data for 2018 as well. But again, there is no update, right? And here is where this guy comes into play. So he's Sanjay, he's not Dan, he's Sanjay. And he joined our group like a year ago, and he had an idea what he was eager and the research, and said, let's try to do this ourselves, right? And then we said, well, like, let's give it a try. And we started looking into how we could do that. And the first thing that crossed that we need the resources, and we looked into how much resources they needed. And I mean, the Google claimed they spent 10 million hours of processing, which seems a bit extensive for the research project, internal research project of a small company. So we said, okay, let's use the credits from Amazon. They are very welcome giving away credits. And the first thing, if you want credits, you need to fill the price calculator so that you can let them know how much it will cost. And we filled these 10 million processing hours in a calculator, and the number was quite large, right? It's $3.9 million. And I kind of said, probably Amazon will not give that many credits. And then we went back to the drawing boards, and we said maybe we can try to make it a bit different. And we started from exactly the opposite side. We said, okay, let's try to make it as cheap as possible using the free tier. And then, like, you get sometimes emails from Amazon asking for a survey. And if you fill it, they give you $25 or $50 of credits, and said, okay, let's do that. And so we had resources fixed. And then we realized that we don't have the knowledge, because we are an IT company and we have no idea about remote sensing and how to do the water. So what we did, we researched the internet, and we found some pretty good papers explaining how you can do this, that made it possible for us to kind of do a similar process ourselves. And then because we didn't have the resources to do it for each and every point in the world, like what Google did, we said, let's focus to the water reservoirs, the ones that are problematic. And luckily, there is also a resource for that. So this is by World Research Institute, an aqueduct product where basically they rank the water reservoirs based on how problematic they are. And we said, let's start from the most problematic ones and then go further down the scale, right? And we did the Blue Dot Water Observatory, which now has 10,000 water bodies. And for each water body, you can see through time how the water extent changes. Like that's the same water reservoir that Cape Town was having problem with, and you can see how the water was really going down in 2017, and then here in 2018 they were like literally in front of the disaster. But then luckily it went up, and now it seems to be much better, right? And you have this Chennai Lake there as well. They unfortunately are not that lucky. You can see that this thing is really going down and seems to be staying there, at least for now. So basically, we base it on Sentinel-2 data because that was easiest for us. The moment we have 10,000 bodies, as mentioned, and we plan to go to 20 or 30,000, something like that. We don't want to go for all the water bodies. Again, the sea that is covering 70% of the globe is not that relevant. And all the lakes in Canada, where there are more than half of them in the world, also for the moment at least, they are not problematic. They are always filled with water. So we are not monitoring those, but we monitor those that are problematic. The process is pretty simple. So this is the IT part, right? We take the Sentinel data, we calculate the cloud mask, we co-register the data, and then we calculate NDWI, so the water index. We do some edge detection, and then we compare it with the data. So like this is NDWI, some thresholding. It's pretty simple, right? Altogether, finding the polygons, and then comparing this with the maximum extent of that specific water body, and you get a result. At the moment, still pretty strange because there are lots of cloud there, but if you filter out the clouds, it seems pretty good. I mean, it's not perfect. You see these bumps here that are probably not real, but I mean, it's not perfect, but it's good enough. And I think that we need to focus to things that are good enough and that they work, right? Now, we did try to look into how we can improve this. So that's an example of a very bad error in the calculation. And what we did is that we established the classification app where people can simply go through these problematic examples and correct our mistakes. So if this was what we planned, and then this is what they see on the image, and then they simply pixel out these things. And that this now then goes into our machine learning process to improve the model, right? And what we did actually is not a rocket science. It's just a bit of a smart engineering. And I mean, it's really nothing spectacular, and it was quite easy to do, really. It took that guy like a month of work, part-time work mostly. It cost us about $400 for the IT resources for initial processing, for the history, and now it costs about $10 per month to actually update the data, right? So in terms of the cloud infrastructure, we are well beyond or well below the 3 millions that we would have spent if we would go for the 10 million processing hours. And I think that's an important point, is that it's really easy now to go into this kind of ventures, to do the project that seems interesting, because you have lots of free data, which is of good quality. I mean, more than any time in the past. The cloud infrastructure is really convenient, that you can do things fast and you scale whenever needed, and then you shut them down. You have lots of machine learning tools that are open source, and you have research papers which kind of guide you through what needs to be done. I mean, that not all are so open that you could really use them. Many are just promoting how good the results are, but there are some which actually have some knowledgeable content in there. And we try to follow these steps as well. So this is the Jupyter notebook for the specific process that we have, that which anyone can take and repeat it. Also, the source code for the backend and frontend of the water observatory is open source, so anyone can do and use it for something similar. And I think the point is that because it's so easy to do these things, we should really do that, right? And we should not just focus to the research projects, but we should try to make things that are operational, maybe not perfect, but good enough. And that we do things that actually build on top of each other, so that we, as a society, we progress. For those who would want to do something like that, I would also recommend to take a look in the EOLearn, which is another open source library that we built for machine learning. Basically, it bridges the gap between the remote sensing data and all the machine learning tools like TensorFlow and the likes, which are not really focused to machine learning. But you can do many steps that are needed to make the data ready for machine learning. Anyway, some links if you want to explore further, and thank you very much.
Dan, that's amazing, and it's really echoes some of the stuff that I'm going to be talking about later as well, like good enough and it works. That's really, really cool to see. And from somebody that's not from Earth observation as well, the things you were saying are sort of ring true with what we've been doing as well, which is great to see that other people are on the same page. One question for you is that the Blue Dot Observatory is an awesome tool, and it can very easily integrate into what we're doing. But how are you considering looking at the Z-axis as well as the extent, and how would you incorporate that?
Sorry, can you repeat it?
So could you incorporate the Z-axis? So obviously a reservoir is not just a flat body; it goes down. So
yeah, I mean, it's not easy to evaluate the depth of the water with the satellite data. So we were looking into using the digital elevation model data and try to take this into account. It's definitely something that we could improve. I'm not sure how far we can get with that, because often I mean, you don't really have the data of the empty reservoir, right? But certainly you could improve it significantly from where we got to.
Interesting.
Cool.
Thanks.
Introduce yourself, Albert.
Okay, will do. All right, so good afternoon, everyone. My name is Jason Barnett. I'm with Booz Allen Hamilton. I support the NASA Langley Atmospheric Science Data Center, their DAC, ASDC DAC, and supporting this ROSAS access proposal called Systematic Data Transformation to enable ArcGIS image services and web coverage services within the NASA Earth Science Data Systems Cloud. Some other folks that are on my team is Matthew Tisdale and Brian Tisdale, who are also with Booz Allen Hamilton, and then Joe Lee, who's with the HDF group. And we've got several collaborators for different science teams, Moppet and Siri science teams, other DACs that are interested in some of the work, as well as the Prediction of Worldwide Energy Resources Power Project. So before I jump into the majority of the presentation, I kind of want to introduce you to a couple different people. So first, this is Peter. Peter's in Spain. Peter uses this app called Solar PE because he's installing a solar panel on his residential home, and the app provides him kind of the information on what he needs to do to size the solar panel and what he needs to get and all of that. And then this is Jill. Jill works for Ferrero, who is kind of a bigger company that owns the makers of Nutella, which is very important to a lot of people. And so Jill does a lot of site suitability analysis for hazelnuts. And then you also have Joshua, who kind of uses a system called PV Systems. It's an architectural engineering software for solar panels. It's a very robust system as well for installing and monitoring a lot of those systems. Then you have Margaret, who has done a lot of work for Africa Rice and global yield crop analysis, doing a lot of different crops and agroclimatology modeling as well. And then you've got Ben, who works for Nokia, and he is trying to estimate a lot of temperature requirements for cooling the batteries and telecom equipment as part of Nokia's kind of renewable energies department. And lastly, you have Samantha, who works for the World Agroforestry, who's looking at different types of climate resiliency models and how you can do different farming techniques throughout Africa. And so my question is, what do all of these folks have in common? And the thing that they do have in common is they're all using NASA Earth Science data through a project called POWER, the Prediction of Worldwide Energy Resources. And what POWER does is it takes a lot of different surface meteorology and solar energy data and brings it together and makes it available to industry, private, academia, just lots of groups throughout the world, and makes it available for them in 3 different kind of areas. It's renewable energies communities. They serve a lot of energy efficient building designs communities, or sustainable buildings, folks that are building buildings and they have to size their heating and cooling systems based off of the climate and the zones in which the buildings are located. And then also biomass crop development industries, or the agroclimatology world, when folks are doing agricultural forecasting. And so POWER really tries to make data, NASA Earth Science data, available to all these communities, with them not necessarily having to go and say download 13,000 net CDFs, unpack them, figure out how to actually use them and understand what the data is. They just may need the solar radiation at their surface, at their location for the last 30 years. And so NASA POWER really tries to help them do that. And so POWER, the reason I bring this up is POWER is one of our collaborators on this project because they use a lot of the data that we're trying to geospatially enable. And they become a broker to then this wide world of users. So with that, though, I had mentioned you can't just take a lot of times NASA Earth Science data and put it in some geospatial software and it'll just work. For example, in this particular image, you may pull in a NASA Earth Science data set and find out, okay, it's upside down, maybe I can flip it, and then all of a sudden you zoom out a little bit and you're like, wait, this data set is showing off the coast of Africa, but it's a globally gridded product. Like, that doesn't make any sense to me. Or a user may pull it in and say, well, this data is upside down, or it's on its side. They're not knowing that the file is actually maybe missing some type of georeference information, or it's just not aligning to a particular CF standard that the geospatial software has to align to match as many data products as possible, or it just comes off, right? You've got it's just offset from it. And it's not saying that the data itself is wrong. It's not wrong at all. It's just that there might be certain pieces in the metadata and stuff that are missing, so the data doesn't work as natively in a lot of geospatial main geospatial software products out there. And so what we're trying to do in this proposal is really look at, as this NASA Earth Science data gets ingested in archives into a system, many of y'all may have heard of the ESDIS Cumulus project. We've had a couple presentations. As the data gets ingested and drops into a Cumulus S3 bucket, it could be 13,000 NetCDF files, but they may not necessarily, those NetCDF files may not just work in a lot of geospatial software. So using the same technology as Cumulus is built on, using the AWS step functions, is like, what kind of workflows can we do to quote unquote fix or transform the data to where it might be putting an OpenDAP with an NCML in front of it using the new DMR++ module. And what that does is it provides the right, attribution to the file, so then we can make a call to it and then output maybe an MRF file or a COG file into another S3 bucket that's then registered within a ArcGIS Mosaic dataset catalog when they're in their geospatial database. And then we can serve it out as an Esri image service out to a lot of these users, specifically one like Power, who is a big component of a lot of Esri products. And so they could consume the image service. They're not actually having to do the transformations, do the fixes, but they're getting a DAC product, maybe aggregated and fixed as an image service, and then can build things on top of that. And then it can also be registered in things like, GeoPlatform, Esri's Living Atlas, NASA's ArcGIS Online, and then just other client services. And you may say, okay, so why are we even interested in GIS? Why do we even do that? Well, in 2018, they put out a survey, the ACSI survey, that says, hey, what are some of the top tools that you guys use to interact with NASA Earth science data? And the users came back and 64% said we use ArcGIS as like our main tool to interact with NASA Earth science data. Then the next 42% say we use QGIS. And then the next one at 32% say we use Envy to interact. These are just some geospatial software platforms that they use. So that's kind of one of the driving factors of saying, okay, what can we do to fix the data to be able to push it out as ArcGIS image services to reach, these 64% of these users that are interacting with NASA data through an ArcGIS platform or a QGIS platform as well. And like I had mentioned, once we get these out as image services, we can then make them discoverable within places like the GeoPlatform, NASA's new ArcGIS Online that they've launched, where you can register the data there, and then users can go there, access it, work with the image services, pull it into their own applications. And then from there, the data is being registered within Esri's Living Atlas, which has a whole nother world of users in academia and K through 12 that know to go to the Living Atlas. And so the idea is not necessarily to create our own catalogs, but to be able to make the data available in a lot of other catalogs that are being used all around the world by folks already, and just to make it more discoverable. So the idea here is you have the data ingested and archived from something like Cumulus, and it drops into S3, right? And then we do the data transformation pipelines that we can do as a DAC to say we need to fix the data a little bit to make it more geospatially ready. And then we provide out what we would consider maybe a DAC analysis ready data set. What we're considering analysis ready, maybe it's just aggregating and it's fixed and it's served out. So then you can also have applied science projects or other folks to do their own analysis ready data. So we're taking it to one point, and that's kind of why I named the slide ARD plus ARD equals ARD. It's kind of been a big conversation this week. Everybody kind of has their own definitions of what analysis ready data is, and it depends on the community. For me, it's getting the data in aggregated format and served out as an image service. But for the Power Project, it's taking that data and it might just be changing the units. And all of a sudden, it's opened up to this whole community of renewable energies because they don't know how to go in and get 13,000 net CDFs and then after that change the units, or how they can take that data and run long-term climatologies and make it into parameters used for solar sizing solar batteries. But that's what they're considering analysis ready data set. And then lastly, I said the data, once it's in those image services, it can be brought into the web mapping applications and worldviews and other applications like Power's data access viewer. It can be used, as everybody talks about, in Jupyter notebooks because of the REST endpoints. And then you can use them in other different web mapping applications and mobile applications. One from the ArcGIS side of the house using their software, because they're just focusing on the large community of ArcGIS users. They can use these ArcGIS image services to build in Esri's web app builder, kind of using their JavaScript APIs and their Python based APIs now within their notebooks, and building with mobile apps and desktop apps as well. And so really the whole idea is, how do we just make NASA Earth science data more available to a lot of these users that are using kind of front-end geospatial application softwares in college, in industry. And so they're getting NASA Earth Science data, and they may not necessarily know that they're using NASA Earth Science data, but at the same time, and if they do, they can get it easier and quicker and do the processing, or just get their location on their, on their phone if they just need to install a solar panel on their house. So that is it. Thank you. Sorry, I had it at 10 minutes, so I wasn't sure how far I was supposed to go. Oh, okay. Okay. Yes.
Some of the applications that you showed here, they also talk about sort of like interoperability and then the convergence, right? Because that's the. Hi. So you talked about like interoperability and convergence of the like some of the ARD, like especially like using through API, right, from the REST API.
Right.
Yeah.
So once we put them out as ArcGIS image services, what's really nice from a power perspective is their web mapping application. They can hit it from a visualization, actually just pull in the image service if they want. I'm trying to find the right slide. If they actually just want an image within their web mapping application, or at the same time, they may have an API, it's a Python API, where they would traditionally maybe go make an OpenDAP call. They could hit the image service REST API call and just get a JSON return. And then they can query those values and do conversions on top of that. And then at the same time, their web mapping application is built with a JavaScript front end. And so they can use a lot of Esri's JavaScript API functions that are already built in to interact with the image service. And what's really helpful for a project like this, where their funding model can sometimes be really small, is they don't have to worry about necessarily designing the entire application and all the responsiveness of it or all the really cool functions up front. They could just interact because of a lot of the things that Esri has built in for the image services automatically. I don't know if that necessarily answers your question, but.
So, okay. So yeah, we actually had a short conversation over lunch today about what is GIS and what is not, but this is more specifically to one of the comments you made earlier. You mentioned that some data was missing from some of the science data files that was necessary for GIS use. And I'd actually say that the data is there, or the information is there in the file, but it may not be specifically what the tool expects. And I think that's a different statement, that we do try and provide enough information in the data files themselves so that they're useful. And the other comment was when you talk about this particular one where the units are different, I guess one of my questions is, on the data provider side, how far should the data provider go in terms of things like tweaking units to match a particular application community, particularly when their primary users are scientific users? So.
Right. No, I'm sorry if I misspoke on saying missing. Like sometimes it might be that the software is looking for it's just following a particular standard, and so the science product may not have the same standard. To say like the units, they may not put degrees north or degrees east in there, or they have called their time dimension something different, which is fine. And that's why we wanted to use something like OpenDAP NCML, so we could try to correct that, and then change it. Change it, modify it so it work within a particular software products. But for your second part of your question, from a DAC perspective, when we're doing it and with science providers, what we're trying to do is say, if it comes in Kelvin, let's put it out in Kelvin. If it comes in watts per meter square, let's put it in watts per meter square, but in a way that it might be 30 years worth aggregated together to where a user like Power, who's an applied science project, knows that their users need it in Celsius, or their users need it in kilowatts meters per square because that's what they're using in their renewable energies. They can do the conversion on their end. If we so choose to say we're going to put a function that you want to pull it in, and we know we're just going to make a unit conversion if it makes their life easier, sure, let's do that. And so it is really more of a conversation. And then at the same time too, it's going back to the science teams as well and saying, hey, science teams, would you be interested in putting together a monthly average product instead of us creating a monthly average product. And of course, that all depends on time and funding and what they need to be doing along the way. So it's really just an open communication line between who's looking for the data. So.
Yeah, a minute ago you just said you could also get output in JSON. Is that coverage data or vector data?
I'm sorry, say that again.
The JSON output, is that for the gridded data or is that for vector data?
So it's all gridded data. And so
Okay.
if you were to use like the REST API endpoint from an image service at like a single location, it's going to bring back, because it's aggregated, a JSON output of like, you know, a series of 30 years worth of values that a user could then do a time series plot or something with if they wanted.
Oh, okay.
Yeah.
You're not returning like an image patch or something. Okay. And
No.
is there a particular format you're using
Format
for the JSON?
So for the image service, I believe it follows a GeoJSON standard, correct? For our ArcGIS image service, yep. And so what the other thing too is what we're also looking at is formats that get served into the image that sits behind the image service. So maybe it's MRF, maybe it's the COGS, maybe it's the CRF model. Maybe it'll eventually be a ZAR if Esri looks to incorporate those as part of behind the image service as well. So you could pull the data sets out too. Uh-huh.
Awesome. It's 12 minutes, right? Roughly. Hi, everyone. I'm Alexis Smith. I'm the CEO of Geospatial, and I'm not a scientist or clever like you guys. I'm a businesswoman, and we founded Geospatial as a brand about 5 years ago. I'm not from the scientific community. I'm a dyslexic dropout, so don't ask me to spell anything, but I'm going to explain a little bit about how we use diversity of thought and how we're using that with Earth observation data to understand bias in data sets. And hopefully that should give you, a slightly different way of looking at stuff. And hopefully you could help us achieve what we want to achieve. So talking about achievements, this is what we've done so far. So we've been lucky enough that we have developed our own technology. So we've developed our own AI, which is it's an unsupervised way of extracting features from remote sense data, so turning rasters into polygons. We've processed 300,000 images to create an orthomosaic for the World Bank for Zanzibar, as well as lots of patents and other things that we've got around autonomous vehicle data and also our automated data pipeline. We're also doing a big project with the European Space Agency and the World Bank, and also some water companies, about completely automating our data pipeline. And when I say our data pipeline is taking what you call a product, we call a raw data. Yeah, so we're sort of further down the usable element. So the stuff that Jason was just talking about, analysis ready data, we call it Amy ready data because it's for Amy. Yeah, but it's the same ARD. Everyone has their own classifications of that. I've been very lucky that we've just won World Geospatial Startup of the Year at the World Geospatial Forum, and lots of other different people have been very nice about the work that we've been doing. So to give you a little bit of understanding of what we're actually doing, we deploy artificial intelligence in unconventional ways to digest, distill, and disseminate that data efficiently, regardless of how imperfect or vast that universe of data becomes. Something that Anna said earlier, there's so much data out there. The issue isn't the data that's there. The issue is about how do you turn that into something useful for people? And that's the bit that we're focusing on. Also, it was mentioned about how imperfect this data could be, and that doesn't necessarily mean that there's missing data in the data products that we're receiving. It might be to do with the interoperability of the metadata or all the other parts that we absorb into our pipeline. So talking about pipelines, we use Earth observation data, so satellite data. So Kelsey from Planet was talking, we use their data in what we do. But we also use IoT data, so that might be sensor data in water networks, as well as things like data from autonomous vehicles we're just about to incorporate as well. And we create the data layers, derived data, and then automated business intelligence. So that is taking the stuff that you very clever people make and turning that into somebody in the field going and fixing a leak in a water system. So we give them the go and do this in this place. But I'm here to talk about bias. So it's quite important that we understand what bias actually is in data. And bias in general is the inclination or prejudice for or against a person or group, especially in a way considered to be unfair. Now, the interesting thing about that statement is that statement itself is biased. So, what is unfair? And it depends on how you classify that. So what we did was we took this the concept of geospatial data and also derived data from Earth observation data and tried to come up with a system that could be useful to understand that bias in that derivation of those data layers, but also could be used for the community that we will open source. Everybody in this room is biased. I'm biased, you're biased, everyone's biased. And that's really important. That's not necessarily a bad thing. If you understand that that bias is there and you can quantify it, it can be useful. So if you are what you know or what you think you know, the objective facts, what confirms your beliefs? So that might be how you were taught. You all got doctorates. I dropped out of university. I think in a slightly different way. So we're both biased in a different way. You probably think in a very structured way. I don't. I think like a scattergun. It's completely ridiculous. And I get told off at work all the time for doing it. But it takes a team of people and a team of different ways of thinking, and that diversity of thought, not just diversity as in sexuality or sex or ethnicity, but education, autism, all these other things that is incredibly important in AI and how we define these things. So explain a little bit about diversity of thought and what that actually means. It's incredibly important that you clever people actively go out and seek out people that don't have doctorates, that aren't what you think is a standard scientist to solve a problem, that you incorporate these people. I was talking to Anna earlier about how how they generate teams of people. Amazing. They get people that's a security person and all these different people all together in a room to solve a problem. That pure diversity of thought is incredibly important, especially when dealing with AI. And that's the way that the whole world is going. AI doesn't lie. AI is a pure form without bias. It's only biased because of the data we put in the system, or how we run the system, or how we QA the system. The AI itself isn't biased. It's how we set it up that makes it that bias. Okay, so this is it's slightly moved around a little bit for the formatting, which is a shame. But this is what we're doing to actually solve this. And this is Bob. So Jason was talking about Peter, Jill, and Margaret. I'm going to talk to you about Bob. Bob the bias. Everything that we have has got a name. It just makes it interesting and it gives it a personality, because these things in essence do have their own personalities and their own biases. So the first thing to do is you have to create a freelance population of people to check your automated system. So we're currently working with the Tanzanian government and the Namibian government, but also groups of people like yourself. One of the things is that I'm an executive board member of the World Geospatial Industry Council, and we're trying to get the message out to scientists, to non-scientists, to everybody, to be part of this freelance population to generate and actually get people's inputs. We then have to generate a baseline. You have to know what you're measuring against. So we've made Bob. Bob is a little app, and it's a gamification. You get to play Tinder, but it's not Tinder with people. It's Bob, which is playing with polygons and Earth observation data. Once you've got that baseline definition, you don't need to have issues around GDPR and about classifying people, and that's really important, especially dealing in the EU. You have to be able to take away the person and just understand the bias behind those people or that generic population. Once you've got each individual population, you can then start comparing them. You can start actually doing clever things and actually comparing them, like Amazon's XGBoost. It's just using standard statistical methods. You can use like a tree ensemble model, but without the ensemble, you just use the tree, and then you can then start looking between each parts of the tree and actually start developing and understanding where things are slanted. It's really important once you've done that to then actually have a feedback loop. So you need to be able to understand what the outputs were and how that feeds back into the machine learning algorithm or into the CNN or whatever you're doing to enable it to then relearn or find new populations. And the last thing is that you need to have this diversity of thought. You have to have the diversity of thought, not only in the development of this and the populations behind it, but the continuing use of it. And that's why we're going to open source this to the community so everybody can use it, because it's really important that things like bias do not affect people in the future. Once you start having derived products from AI, and those derived products sit on other derived products, which sit on other derived products, which in the future will happen, you could be in a very, very sad situation where you have some erroneous negative on a negative output that could create a data crash. You could have something really horrible go wrong. An ambulance could go down the wrong road. You know, somebody might not be evacuated from a flood extent. People might die. You could have issues behind that because you have the wrong dormant subliminal bias within your data sets you don't understand. And it's important that we all tackle this now rather than thinking about it in the future when it becomes a problem. So things like the interoperability of metadata, the things like how everybody talks and how everybody communicates between, not just within each individual sector, but between other sectors. So Earth observation to geospatial to autonomous vehicle, you know, everybody all together needs to have this complete understanding and this interoperability of the metadata behind it. That metadata also needs to include things like the source data. So how did you derive that product? How did that come from? Where did it come from? Not just what it is, where's it come from? Who owns it? What's the licensing? All these other things need to be thought about. Otherwise, there will be a problem in the future. So I've got like a minute and a half, and I'm going to show you something a little bit more technical because I know you guys like this type of stuff. So this, in essence, is what we're doing. We're finding the sort of cool technical parts and the sort of the edge cases out the standard deviation curves. And this is Bob. So in essence, what Bob is we extract features using Amy, and we actually create these the polygons. We put them into individual packets, and then we've developed our own automated validation process, which works not off an object-based, but a pixel-based QA against each other. Now, what we then do is, because of the increase in the population sizes, we then have to look at that and actually get people to play the game, play Bob in different countries, and use the different populations and the different answers to come back into what we're then doing, to then go feed back into the original extraction at the start. This is going to be done over the next few months. We've got lots of people that are going to be involved in this. And if anybody wants to please get it involved, I would really appreciate it. So please follow us on Twitter. But this is my last point, which is really important. AI biases will explode. So everything you're doing, no matter if you think you're not doing it or there isn't bias, there might be dormant biases in what you are doing. And that's incredibly important to understand. Nobody in this world is perfect. Everybody has their biases and their little differences. And that's an amazingly beautiful and amazingly good thing if we use it properly. The only unbiased AI and the only unbiased businesses will survive, and that includes the unbiased data products that you guys are generating. So please do get involved and remember Bob, the bias. Thank you very much.
And everybody's in time. Yeah, please introduce yourself. Okay.
Hello, I am Dan Pallone, and I'm going to talk about improving communication in a disaster scenario, and specifically with the Snowball Edge. I'm going to jump right in here. So if you're not familiar with the Snowball Edge, it looks like that. It's roughly maybe that big, about that high, and it's a ruggedized box. It was introduced at reInvent in 2016, and it's basically onboard storage, onboard compute. You can think of it as a data center in a box. But what makes this thing particularly interesting to us is that the storage, the compute, they're all exposed as AWS services. So storage looks like S3, compute looks like EC2. The takeaway is that basically you can take an application that was built for the cloud, package it up, put it on a box, and then ship it wherever it needs to go. Amazon actually treats these as freight, and you can provision them automatically and they can be distributed. Okay, so that is context. I want to step back. What I'm going to talk about is ultimately this application. This is a processing stack and a front-end application we call Headlamp. And the idea is to provide information into a disaster response scenario. It's a real simple interface, and to kind of get to how we got here, I want to step back and talk about an actual disaster, the California Camp Fires. So in November 8th, 2018, 7 a.m., a pager goes off for a Butte County search and rescue responder. He was on a conference call at the time. An hour later, when the conference call ended, 8 a.m., he turned on his radio, and the first thing he heard was that the fire was everywhere. The person I'm talking about, his name's Trevor Skaggs. That's him in yellow with the really cool beard. And he was a volunteer for the search and rescue and for the North Valley Animal Disaster Group. What we had a chance to talk to him, we're working with AWS, we had been doing a disaster response user needs survey. We got connected to him and had a chance to sit down and interview him and really get some feedback. The feedback coming out of talking with him fundamentally changed how we approach this disaster response pipeline. So to give you some idea, this is a map of Northern California. The red area up there in the corner is the initial fire area. So 7:20 a.m., there's an evacuation order from the Butte County Sheriff Department for Polga, for the town of Polga. It's right there. 40 minutes later, there's a follow-up tweet. The evacuation order gets extended out to Paradise East, all the way to Highway 70. 40 minutes after that, there's another one that takes out zones 2, 6, 7, and 13. 10:20, give or take, another tweet comes out from the Sheriff Department. Centerville, Butte Creek areas are under evacuation orders. Okay, by 1 o'clock that afternoon, CAL FIRE puts out a tweet. In this tweet, 8,000 acres have burned. The fire is 0% contained, and evacuation orders are underway for Paradise, Magnolia, Concau, Butte Creek Canyon, and Butte Valley. So I want to put this in context, right? This is 6-ish hours after that initial tweet. This is the footprint of Washington, D.C. The city of Tacoma isn't much smaller than this. It's roughly the same size. It's like 68 square miles versus 62 square miles. In 6 hours, it had gone from an initial tweet, an initial emergency alert, to having either an area the size of about twice the size of DC or twice the size of Tacoma had either burned to the ground or was about to. By numbers, on that first 3 hours, 5,000 acres burned. 24 hours, you're up to 70,000 acres. The end of the first day, there's almost 2,300 people on site responding to this. A combination, law enforcement, first responders, search and rescue, fire, et cetera. By 9 p.m. that night, Trevor, the individual we were talking to, gets pulled in and start doing some GIS mapping. At this point, they've had evacuation routes cut off. The fire is moving so fast, they've had to move people multiple times. They evacuate them out of one location. That now becomes threatened. They have to re-evacuate these people into a different location. What they needed, and this we heard this loud and clear, is I need a map on the wall with a big red area that says fire is here, don't go there. And like that was the level that everybody's operating at. In those first 24 hours, you've got teams trying to contain the fire. You have evacuations of people multiple times. You have evacuations of animals when you can. Some of these, and not just like dogs and cats, we're talking horses, cows, like livestock that are difficult to move. You have traffic management and traffic rerouting. You have search and rescue operations, and you have public communication activities that are going on trying to get this information out, telling people where they need to be. And the whole time this is happening, you're talking to individuals who are legitimately wondering if everything they own just burned to the ground. Communication, clarity, surfacing that as information is absolutely vital. So I mentioned the user needs study. We talked to Red Cross, we talked to Mercy Corps, we talked to Doctors Without Borders. There's a number of them. It's available at that URL. You can just pull it down. But there were a number of takeaways we got out of that. One of them is there's intermediate communication issues, but there is communication capabilities. It might just be in situ. It might be a mesh network sitting in the actual environment. There may be reachback capability. There might be periodic reachback capability, but there is communication, but with communication issues. You have to be able to support analog field work. That was absolutely vital. There's a whole separate talk you can do on that. It's really fascinating, some of the analog solutions you can bring in. But some of the two pieces that I want to talk about here are there's a large community of open source projects that exist to support this. There's a lot of work has gone into building very specific applications that solve very specific needs. And you can't come into this environment thinking, oh, I'm going to build this solution that'll solve everything for everybody. People are trained on very specific solutions that, and in a good way, that solve their need. And then the ability to push compute and to push this data out into the field was key. That was a huge piece of an advancement that could be made to push that out there. So we stepped back and we looked at this again and we said, all right, how do we make day one easier? What can we do here? And our first takeaway, particularly after talking to Trevor, is that we needed an extremely rapid response capability. We cannot get them a box. So that Snowball Edge I showed you in the beginning has a lot of great potential, but we couldn't, there's no way we could get that in there in the first 6 hours of a fire. It was not an option. We need to get them easy access to remote sensing data. That was key. It has to be on a basic map foundation. Everybody's operating off of maps, and it needs to be a really simple interface. We need to be able to show this. We have to have flexibility to pull in from disparate data sources. There's open data from government agencies, there's open data from commercial agencies. We need to be able to pull in the relevant information and make that accessible. Stepping down a little bit later, once you get past that initial kind of day one piece, if we can get integration with familiar tooling, simple interfaces, 15 minutes was the key. That was what he clearly conveyed. If I need more than 15 minutes to teach somebody how to use this thing, it's not gonna happen. So give me the interfaces we can learn in 15 minutes, use familiar tools if you can, and the ability to run this offline and then sync back and update this periodically as we go. So we put together this disaster response processing pipeline. Starts out with an event trigger. It can be an automated trigger, USGS earthquake, NOAA hurricane alert, or it can be human triggered. Like there's a fire here and we're going to trigger this. Once that starts, everything spins up and we can start pulling data in parallel from multiple data sources, open data sources. As that data is being put together, we can stand up a set of interfaces. As long as they have network connectivity, because we can do this in the cloud, we can push that URL out immediately. And within minutes of that initial alert, we can start surfacing this data out there. There's nothing, like it's immediately accessible. The next step, this SBE, that's where the Snowball Edge comes in. Because we've done all this in kind of standard set of AWS services, we can take this whole thing, package it up and drop it onto a Snowball Edge. And this can all be done automatically. You can provision these. We can push this out there and it's basically that chunk of time, whatever data we're able to process up until the point that this thing gets deployed, we can chip out, drop onto the Snowball Edge and push in situ. Once this thing's there, as long as they have power, you can be then using this information in situ and continue to add to it because we can push this whole stack onto that Snowball Edge. We can pull imagery off of drones. You can, obviously images from cameras, those can all be incorporated. And you can go all the way to the extreme if you have a remote ground station. So Maxar has an option here, AWS Ground Station has an option here. If you have a remote ground station and you can get an overpass, you can actually do a downlink in situ of the current data and process that in right there in that stack and surface it. You can leverage this to help prioritize and filter data. You're not trying to replace the experts. You're not trying to replace those people on scene. You're trying to help them filter that and prioritize that deluge of information that's available. I'm not going to go into this in detail, but architecturally it looks like this. One of the big things to kind of take away is that it's almost entirely serverless. And the idea being when it's not in use, it doesn't cost us anything. This whole thing spins back down to roughly zero. But when it is, when something does happen and this does spin up, it spins out horizontally. And we can scale this out as much as necessary to start pulling products in. To give you an idea what it looks like, this is OpenStreetMap as the base layer you're looking at there. Again, chipped out. This is all functional offline. You can zoom in and out. What you're seeing is the fire boundary, and then you're seeing NASA VIIRS data. So this is fire data being overlaid on top of this to give you a sense of where, like based on the latest data we have from VIIRS, this is what we're actually seeing. This is an overlay. In the event of a disaster response, there's a number of commercial companies that make available public data for that disaster area. This is Maxar imagery. Maxar stages a bunch of data, Planet does as well. This is pulling that scene and overlaying it on top of that OpenStreetMap, and this is basically as current as we can get from these commercial providers. Earlier, there was a talk from Planet with the high repeat rate from the Dove satellites. As long as they're making that available in the disaster response program, we can pull that and surface it here. What you're seeing is smoke here. This is actually, if you zoom, if you see the whole scene, this is the smoke pulling over. This is a SWIR imagery, shortwave infrared. And in this one, if you can see it in the corner there, you can actually see homes burning, like this is a neighborhood on fire. But this is the kind of imagery that's available. This is the kind of data that's available. And if we can surface it, if we can get to it fast enough, we can surface it in a very simple way. And then this can synchronize back. So at the end of the day, where I'm going, the Snowball Edge gives us the ability to push this out to the actual first responders, put this into, in situ. But the key piece is decreasing that cognitive overhead and that time to learn. It has to be simple. You have to take this data, make it usable, make it approachable, because they have a job to do. This is the piece of information informing them, but ultimately they're dealing with an honest life and death scenario. So by way of challenges and opportunities, kind of the call to action here, we always need more programmatically accessible open data. If we have to call somebody, if somebody has to ask somebody as a human to get involved and produce this data, there's a huge lag time versus being able to respond in minutes and actually pulling data as soon as it's available. If you are working on an open source project, or if you are funding an open source project, I can't beg enough how important documentation and solid deployment information is. There are a lot of great tools out there that the barrier of entry to just getting them surfaced is really difficult. So please, if you're involved in these, don't let that effort and all of the investment that went into that fall to the side because nobody can figure out how to deploy it. So please engage there. And then ultimately, if this is something that's of interest to you, we're looking for help in getting this out in exercise environments or field campaign kind of scenarios because the time to take this out is not in, or to test something new is not in an actual emergency. So if this is something, please find me. I'm happy to talk afterwards. Okay, that's it.
So I didn't catch, is the capabilities available then that the responder is able to draw the fire boundaries and make that kind of next level actionable information, or are you guys doing any of that kind of rapid processing for them? Is this really their environment to do what they need with it to, put out boundaries and creating, be it shape files or something else?
Yeah, so it's both or either is kind of the, so when we would first provision one and stand it up in AWS, the button down there says sync. This view is from the Snowball Edge, but on the cloud side of this, that blue button in the bottom corner basically lets you configure, I need to package this and put it out there. And that's where you would select, we generally have your area of interest and time of interest, but you could configure that, the layers you want to push out there, and then additional products. So those open source pieces I mentioned, like I want to include this, and include this. And then you can hit a button and that will package up what will eventually be deployed on the Snowball Edge. When you hit this on the edge, you get this view where you can turn those on and off, and you can hit the sync button to, if you have connectivity, fetch the latest, because the cloud side keeps running. So we can continue populating that data and pulling current data. And as soon as you can get connectivity to the box, it can reach back and sync it forward again.
Okay, thanks.
Thanks for the great presentation and also the efforts. I have a question regarding kind of post-disaster and recovery. So I've seen some folks who've done a lot of, who did the assessment of the campfire after. And one of their biggest challenges was getting that data from the campfire, collecting terabytes of data and getting that to people to see if their homes were still, to see if their homes were still there. Would this work as well? So they'd be able to put that data locally, but their biggest challenge was they were not able to get the data off of a UAV and into the cloud. They were actually, I think they were driving it down to Sacramento.
Yeah, in addition, an additional use case to not just kind of doing that assessment, but training and replaying scenarios. So, here's how the campfire unfolded, here's what we actually saw, and using that in training exercises for first responders to be able to react, to simulate that, know what actually happened and how it unfolded. I would very much like to have this as part of that. It doesn't do it now, but there's no, like basically that data can be put onto the Snowball Edge, but we don't have anything right now that then takes that and repackages that into something that's playable, but there's nothing preventing, like if someone were using this and pulling that and capturing that data, it would be on the edge that you could then bring back and pull back off. Yeah.
Chrome at some point. So what's the best way to do that?
Yeah, you just have to go and get out. Yeah, get out of the slide mode.
Okay.
Escape.
Hi everyone, I'm Namrata Malarat from Jet Propulsion Laboratory. I'm a software engineer and I work on building up science data systems. So I'll be bringing a more technical flavor to the session. So my talk is about keeping up with the acquisitions. So I'll be focusing on the upstream ancillary ingestion. I work on a project called ARIA, and our main job is to respond to urgent events like earthquakes, fires, floods. So we do rapid large-scale analysis on SAR data, and we want to get higher level actionable information out to the urgent response teams so that they can utilize this information to better focus their rescue missions or their efforts. So time is of the essence. And later on, I'll dive into our pipeline, which will show you how extremely essential it is to make sure that we have all of the ancillaries in our system beforehand to make sure that we can get these products cranked out as soon as possible. So I'm very quickly going to give you some context about the ARIA project. So we produce surface displacement maps and damage maps, flood maps. Our system, I'm going to very quickly show you our website. So our system actually uses HiSDS, which is a hybrid science data system. So we use a combination of on-premise and cloud infrastructure to run our processing system. So, oops. Okay. All right, so this is our official website. So I'll start out with the first one here. So you can see this is a ground deformation map from the Oaxaca earthquake in Mexico that was of 7.2 magnitude. This is the early phases of the Kilauea volcano eruption from 2018. Then we've got the damage proxy maps from Hurricane Maria and Irma that had affected the East Coast and Puerto Rico. We responded to the Roboso earthquake in Mexico, and there are so many examples here, and I'll show you. We have been continuously responding to all of the California wildfires, and we did also recently respond to the Ridgecrest earthquake in California. So this is just to set some context for you all. And I'll be jumping back to my presentation. All right. So yeah, why keep up? What is the impact? So this is a very simplified version of our standard products pipeline. You can see the very first thing up here is the ancillary ingest. If you could, this is a data-driven pipeline. So the production of the availability of ancillaries, the production of intermediate products is what drives the pipeline forward. And our readiness to produce products is determined based off of the geospatial coverage over the area of impact. So this is a visualization of the acquisitions for the Ridgecrest earthquake. So once we know that, okay, we're ready to go, we want to immediately have our system jump into action. And everything is automated, so there is no operator in the loop. So we need to make sure that our system is continuously keeping up and getting all the SAR data into our system. What is the challenge with that? We have external dependencies, right? Because we need to get all of the information from ESA's Sci-Hub, and we do also rely on NASA's ASF. And because of the nature of our infrastructure, right, we're using cloud technology, so we have hundreds of workers running at the same time. So this brings a very dynamic nature to our processing system. So the challenge is to ensure that the ancillary ingest subsystem is reliable. So this is more of a technical take on things. How are we going to address any failures that we end up having during this ingest process? What do we do to account for external service downtime? How are we going to handle edge cases? And what do we do in case our system is overloaded with duplicate jobs? This may seem very low level and very focused on a technical aspect of things, but again, I'd like to highlight that if these things are not in check, if we haven't covered our bases with these, then there is no use if we are late in our production. Those products will no longer be useful because, again, there are other agencies, there are other efforts trying to do the exact same thing, right? Trying to get out information in time so that we can help people. So the answer to that is we want to build in the resiliency and the robustness into our system in the processing side of things. So I'll dive more into what we are exactly doing. So I've just quickly noted our answers to all of these questions. So handling failures, we automatically retry. How do we ensure for downtimes? We use a sliding window approach. And what do we do for edge cases? Mature the system as much as possible. And what do we do about duplicate jobs? The first man wins. So I'll dive more into all of these approaches. So here we have the overview. We have scrapers continuously running. When you think scrapers, the first thing you would think is website scraping, which we do in case of getting orbits into our system. But when it comes to acquisitions and the IPFs, IPFs are instrument processing facilities. So these provide us with information about the auxiliary information content of the acquisitions themselves. And this is important. I will tell you why later. So we are querying Sci-Hub and ASF and continually ingesting precision orbits, restituted orbits, and acquisitions. Why do we do so? Because we want fast local access. We don't want to have the latency of saying, oh, you know what, there's an earthquake. We should probably look for what acquisitions are over this area. We don't want to lose time there. So we want to store the metadata so we can immediately know the answers and immediately start downloading the SAR data to kick off our processing. So which data provider do I go to? This again, are latencies. So ESA maintains a hot cache and a long-term archive. So anything older than 2 years is moved to the long-term archive. So if we are doing long-term monitoring, like in the case of, we do have a machine learning project for monitoring land displacement in certain European countries. And this is, we're hoping to help predict landslides for that project. So when it is long-term like that, and you're looking back further back than just 2 years, then we want to be able to get the data soon again. So in that case, we go to ASF. So keep-ups and hold-ups. We know where to get the information from, so what is the problem? It is the keep-up mode. So with acquisitions, it's a best efforts job. Let's get as much information into our system as possible as we are going through time. So what happens if there's a downtime? What if Sci-Hub is down, right? It may be down for the last couple of hours. So do we just not get that information into our system and keep moving on? That's not an option when it comes to urgent response. So we use the sliding window sort of an approach. So anytime we are saying, okay, give me information, look back in the past 5 hours and give me everything. And you might say, well, you're still going to miss some acquisitions if there was service downtime. How do you account for that? We have a different type of job, which is a daily look back. So it says, I will run daily and look back 5 hours and give me everything that doesn't exist in my system. So we are doing our best to make sure that we have all the information at all times. Here's one of the biggest challenges that we're working with, reprocessed acquisitions. So ESA does reprocess and update some metadata, and also does update the IPFs. The IPF versioning is important because when you want to create damage proxy maps, you want to make sure that you are using the best or at least comparable versions of the acquisitions to produce these products. So we want to make sure we have the latest version of even a reprocessed acquisition. We don't want to be working with the deprecated version. So when these changes happen, there is a change in the hash. So the acquisition ID itself has a certain naming convention that ESA has standardized. So it does have a hash. And sometimes when they are reprocessed, there is a change of minute couple seconds in the start and end time. So what's the problem if they're reprocessing? Well, how do we know which acquisition has been superseded? Unfortunately, within the metadata, there is no information that tells us, oh, you know what, this is a newer one, that this is the ID of the older one. So that would tell us enough information saying, okay, fine, we're disregarding that. But we don't know because that information is not available. Sci-Hub stores the original acquisition and the reprocessed acquisition as well. ASF, however, gets rid of the older acquisition and only keeps the latest. So when we are trying to get information about the IPF for an acquisition that, say, is older than 2 years, what do? We go to ASF because they have that long-time archive. But if we are querying for a deprecated acquisition, it says, I don't have it. So now here's the challenge. If I get an empty response from ASF, does that inherently apply that it being an empty response guarantees that it's a deleted acquisition? No, because there are certain scenarios that through experience I realized getting an empty response from ASF could mean a variety of things. There could be an issue with them interacting with CMR and giving back a valid response. That results in empty. Sometimes the acquisition doesn't exist. Yes, one reason is that it was superseded. The other reason is that they did not ingest it yet. And funny thing is, we get a 200 status, not a 404. So it doesn't guarantee anything. So as I said, handling the deprecation is still in progress. When it comes to just a change in the hash, we are able to handle it because the rest of the ID looks similar, so it works into our logic. Now comes the challenge of running in the cloud environment. So our SDS is designed in a way that we run all of our product generation executables in the cloud in Docker containers. So they all run in parallel. We use auto scaling depending on the volume of our processing request. So when it comes to urgent response, we want to crank up as fast as possible. So we set higher limits on our auto scaling to our whatever maximum we see fit with our budget. And we are storing our data on S3 so that we can make it easily available to the scientists and people who want to access our products. Our end users are not only scientists, but also agencies like FEMA. Now, running in the auto-scaling environment, we need to be mindful of connection limitations. As we are talking to external sources, Sci-Hub has limited to 2 connections per account. So we have decided to run jobs where we need to be talking to Sci-Hub on premise, so there's no need for scaling. Whereas ASF doesn't have any limitations, so we can scale up our jobs to tens and hundreds and crank through them. This is a little bit more of a technical detail, but I will give you an overview. Within our team, from our experience, we have seen different types of edge cases, and we like to classify them into transient and non-transient. For us, transient means if we end up retrying this in a bit or immediately, it's going to go through. So our efforts to get information about the acquisitions or the acquisition itself will be successful. So in case of the transient errors, we like to handle them with a feature of the SDS. We have automated retries. So it can say if a certain job of a certain type is erroring out with this set of specific errors, go ahead and automatically retry them. This saves time of an operator going in and saying, oh, Sci-Hub's been down for a while, we should maybe do something. Or we see this error, I think I should handle it. So that is how we are handling that situation. Now, when it comes to auto-scaling, we say, well, we've covered handling of the failed jobs, so we're good, right? But no, when you end up with this automated system plus multiple jobs being picked up, we end up with a lot of duplicates in our system. So the solution to that is short-circuiting the jobs. So the first man wins. If there are other jobs trying to do the exact same thing, trying to retrieve the IPF value for a very specific acquisition, the other ones are going to say, someone else did the job, I don't need to run anymore. I'm not going to proceed. This is a much more detailed approach of short-circuiting. As we are retrying, we do maintain context within the job, saying how many times it has been retried, and we like to set a cap, saying you can only do a max of 10, and then stop trying. So if anyone is interested, you can go through the slides, and there is a very detailed information about the logic that we are using to do so. So the takeaway is building in robustness and resiliency when you have latency requirements on your system and when time is of the essence, like for the ARIA project. And this is basically reiterating everything that I talked about in the previous slides. So questions?
Thank you, everyone. I think it's been an awesome presentations, and thanks to all. I would like to give a round of applause to all the presenters. And I also would like to thank my conveners, Anna and Joe, as well, for helping me out with this one. It was an awesome job. Thank you very much, and have a pleasant ESIP.